Thank you for joining us for this learning path on packaging your AWS Lambda functions as container images. My name's Rob Sutter. I'm a senior developer advocate with the Serverless team here at AWS, and I'll be leading you through these 6 videos. The first video is today's, understanding how the AWS Lambda service invokes your functions. This will give you some background information on AWS Lambda. Now, you won't necessarily need this information to implement and run your Lambda functions, but it should help you understand a little better the differences between packaging as zip, archive file formats, and container image formats. In a follow-on session, we'll discuss the Open Container Initiative or OCI format. We'll learn how to deploy your Lambda functions packaged as container images using the AWS Lambda console. You'll learn how to deploy them from the command line using the AWS SAM CLI. You'll learn how to optimize those images for deployment that's more quick and more control. And finally, you'll learn some special considerations when you package your Lambda functions as container images. In this session, you'll learn about the underlying hardware that AWS Lambda runs on. You'll learn about Firecracker, the lightweight virtual machine manager that AWS purpose-built for AWS Fargate and the AWS Lambda environments. You'll learn about micro virtual machines and how those load the operating system for your functions, what operating systems you can run inside micro VMs, and finally, you'll learn what Lambda runtimes are available to you. So to start with, there's an underlying hardware piece associated with your Lambda functions. As is often said, yes, there are still servers in serverless. That underlying hardware is called a Lambda worker. Lambda workers are bare metal EC2 Nitro instances. Now, the Nitro system provides a number of features for Lambda functions, including enhanced security and better isolation between environments. Lambda worker instances have a maximum lease lifetime of 14 hours. That means from the time they're first deployed until the time they're retired out of the fleet is only ever 14 hours. This is another security mechanism and enforces underlying patching in treating the infrastructure as immutable. For additional information on the EC2 Nitro system, please visit the URL shown on this slide, s12d.com/nitro. Firecracker is the lightweight virtual machine manager purpose-built for AWS Fargate and AWS Lambda. Firecracker is an open source virtualization technology. You can review the source yourself and make contributions on GitHub. Firecracker was purpose-built for multi-tenancy workloads and enhances those strong isolation guarantees provided by EC2 Nitro. Firecracker employs a minimalist design philosophy. Anything that wasn't needed to run Lambda functions and Fargate containers was stripped out. This resulted in 96% fewer lines of code than in QEMU, which it replaces. And Firecracker supports running any Linux guest OS as long as the kernel is version 4.14 or greater. For more information on Firecracker, see the reference shown on this slide, s12d.com/Firecracker. Visually, the Firecracker environment looks like this. You have a bare metal server, that's that EC2 Nitro instance that we referred to before. And on top of that, there's a host kernel space. You can think of this as Firecracker as an OS, but it's actually KVM. On top of that, you have a number of guest OSs and container workloads. Now, as you see on the slide, Firecracker scales to thousands of multi-tenant micro VMs on a single instance. Inside each workload, there is a control plane shown on the right side of this slide. That control plane is accessed by the client via REST API, and it controls services such as networking, storage, rate limits, and metadata. Now, each of those tasks shown on the previous slide was itself a micro VM. And a micro VM is the Firecracker isolation boundary. Micro VMs were chosen over containers because of those stronger isolation guarantees they provide. and they were chosen instead of traditional VMs because of the rapid startup time they provide. With the combination of Nitro instances, Firecracker, and micro VMs, makes it safe to run multiple functions from multiple tenants on the same hardware. And the lightweight nature of the micro VMs means that you can run thousands of functions on a single instance. The performance of micro VMs is similar to native operating, and that's because of that lightweight overhead that was a design goal when Firecracker was created. But they didn't sacrifice universality when creating it. Firecracker supports arbitrary Linux binaries and libraries so that you can run the tools that you need inside AWS Lambda. And finally, micro VMs, because of their lightweight nature, start up quick and clean up quickly as well. All of this results in less cost to you, the customer, while providing you with greater performance. For deep details on the structure of Firecracker, including the isolation mechanisms and performance characteristics, please see this white paper shown on the slide, s12d.com/firecracker-whitepaper. Up until this point, the AWS Lambda service stack is the same whether you deploy your functions as zip file archives or as container images. It's at the operating system level that the experience begins to diverge. Deploying your functions as zip file archives is the traditional AWS Lambda experience. When you do this, you get an underlying operating system that is fully managed by the AWS Lambda service. This means that updates happen automatically, and they're transparent to you, the end user. In practice, the underlying operating system is either Amazon Linux or Amazon Linux 2, depending on the specific runtime that you choose to deploy. These underlying images also include additional AWS-specific packages and configurations that are most frequently needed when running workloads on AWS, so that you don't need to package or install them yourself. For more information on Amazon Linux, please see aws.amazon.com/amazon-linux-2. When you package your Lambda functions as a container image, you gain some measure of control, but that also comes with some measure of responsibility. Whereas zip files the operating system under zip files are fully managed by AWS Lambda, in container image functions, you, the customer, provide the entire operating system. This means that you're also responsible for updating that underlying image, including security patches, kernel patches, and other updates that you need to apply. And when you update these underlying images, you need to redeploy your function as well. When you deploy your Lambda functions as zip files, the underlying operating system will always be Amazon Linux or Amazon Linux 2. But when you deploy as container images, you can run any Linux operating system with a kernel of 4.14 or greater. Finally, the packages that are deployed on Amazon Linux are not going to be there on images that you build unless you install them yourself. This means that everything that you expect to be inside that image, you need to put there yourself. Runtimes are also different between the zip file and the container image experience. Runtimes are nothing more than language-specific environments for running your functions. In the case of an interpreted language, such as Node.js, it's the interpreter itself and the standard libraries. Now, these versions and libraries are managed by AWS Lambda for you. We currently offer 6 managed runtimes that you see here on the slide: Node.js, Python, Java, Go, .NET, and Ruby. AWS also offers custom runtimes for other languages. When you package your function as a zip file, your function is added to the runtime, which is on top of the Amazon Linux operating system. For more information on Lambda runtimes, please see this URL available on the slide at s12d.com/lambda-runtimes. When you package your functions as container images, you must provide the runtime yourself. AWS Lambda provides a number of base images that include the Lambda runtime for you to help you get started. and those are provided for the same 6 runtimes that were shown for zip files. However, you can create container images from any supported base image. When you do this, your container image includes everything from the operating system all the way up through your function code. And in fact, when it's deployed, the container image becomes the entire file system for the Firecracker micro VM. You can find the base images that are provided by AWS Lambda at gallery.ecr.aws by searching for Lambda. So a quick review of this prologue. You learned a bit about the AWS underlying hardware that's used to provide Lambda worker instances. A brief overview of Firecracker, the virtual machine manager, and micro VMs, the isolation boundary inside Firecracker. You learned about the valid operating systems for AWS Lambda and how they differ between zip file and container image formats. And you learned about the various runtimes that are available for AWS Lambda, as well as your ability to build your own. So when seen as a whole, this slide shows you 2 customer functions running on the same machine or the same worker instance, but with strong isolation guarantees from top to bottom. For some additional resources on all of the topics covered in this session, please see the links here on this slide. In the next session, we'll go over the Open Container Image Initiative format, or OCI format, and discuss its impact on your functions. I hope you've learned something. For more information on this and all serverless topics, please visit us at serverlessland.com.